Why are we still using CPUs instead of PUS? It seems to me that these days lots of calculations are done on the GPU. Obviously graphics are done there, but using CUDA and the like, hashing algorithms, think bitcoins, and others are also done on the GPU. Why can't we just get rid of the CPU and use the GPU on its own? What makes the GPU so much faster than the CPU?
TL, Doctor Answer. PUS have far more processor cores than PUS, but because each PU core runs significantly slower than a CPU core and do not have the features needed for modern operating systems, they are not appropriate for performing most of the processing in everyday computing. They are most suited to compute-intensive operations such as video processing and physics simulations. GPU is still a relatively new concept. PUS were initially used for rendering graphics only. As technology advanced, the large number of cores in PUS relative to PUS was exploited by developing computational capabilities for PUS so that they can process many parallel streams of data simultaneously, no matter what that data may be. While PUS can have hundreds or even thousands of stream processors, they each run slower than a CPU core and have fewer features, even if they are Turing complete and can be programmed to run any program a CPU can run. Features missing from PUS include interrupts and virtual memory, which are required to implement a modern operating system. In other words, PUS and PUS have significantly different architectures that make them better suited to different tasks. A PU can handle large amounts of data in many streams, performing relatively simple operations on them, but is ill suited to heavy or complex processing on a single or few streams of data. A CPU is much faster on a per core basis, in terms of instructions per second, and can perform complex operations on a single or few streams of data more easily, but cannot efficiently handle many streams simultaneously. As a result, PUS are not suited to handle tasks that do not significantly benefit from or cannot be parallelized, including many common consumer applications such as word processors. Furthermore, PUS use a fundamentally different architecture. One would have to program an application specifically for a PU for it to work, and significantly different techniques are required to program PUS. These different techniques include new programming languages, modifications to existing languages, and new programming paradigms that are better suited to expressing a computation as a parallel operation to be performed by many stream processors. For more information on the techniques needed to program PUS, see the Wikipedia articles on stream processing and parallel computing. Modern PUS are capable of performing vector operations and floating point arithmetic, with the latest cards capable of manipulating double precision floating point numbers. Frameworks such as CUDA and OpenCL enable programs to be written for PUS, and the nature of PUS make them most suited to highly parallelizable operations, such as in scientific computing, where a series of specialized PU compute cards can be a viable replacement for a small compute cluster as in NVIDIA Tesla personal supercomputers. Consumers with modern PUS who are experienced with folding at home can use them to contribute with PU clients, which can perform protein folding simulations at very high speeds and contribute more work to the project. Be sure to read the facts first, especially those related to PUS. PUS can also enable better physics simulation in video games using FESCs, accelerate video encoding and decoding, and perform other compute-intensive tasks. It is these types of tasks that PUS are most suited to performing. AMD is pioneering a processor design called the Accelerated Processing Unit, APU, which combines conventional x86 CPU cores with PUS. This approach enables graphical performance vastly superior to motherboard integrated graphics solutions, though no match for more expensive discrete PUS, and allows for a compact, low-cost system with good multimedia performance without the need for a separate PU. The latest Intel processors also offer on-chip integrated graphics, although competitive integrated CPU performance is currently limited to the few chips with Intel Iris Pro graphics. As technology continues to advance, we will see an increasing degree of convergence of these once separate parts. AMD envisions a future where the CPU and CPU are one, capable of seamlessly working together on the same task. Nonetheless, many tasks performed by PC operating systems and applications are still better suited to CPUs, and much work is needed to accelerate a program using a CPU. Since so much existing software uses the x86 architecture, and because CPUs require different programming techniques and are missing several important features needed for operating systems, a general transition from CPU to CPU for everyday computing is very difficult.
What makes the CPU so much faster than the CPU? The CPU is not faster than the CPU. CPU and CPU are designed with two different goals, with different trade-offs, so they have different performance characteristics. Certain tasks are faster in a CPU while other tasks are faster computed in a CPU. The CPU excels at doing complex manipulations to a small set of data, the CPU excels at doing simple manipulations to a large set of data. The CPU is a special-purpose CPU, designed so that a single instruction works over a large block of data, sim/single instruction multiple data, all of them applying the same operation. Working in blocks of data is certainly more efficient than working with a single cell at a time because there is a much reduced overhead in decoding the instructions. However, working in large blocks means there are more parallel working units, so it uses much more transistors to implement a single CPU instruction, causing physical size constraint, using more energy, and producing more heat. The CPU is designed to execute a single instruction on a single datum as quickly as possible. Since it only needs to work with a single datum, the number of transistors that is required to implement a single instruction is much less, so a CPU can afford to have a larger instruction set, a more complex ALU, a better branch prediction, better virtualized architecture, and a more sophisticated caching/pipeline schemes. Its instruction cycles is also faster. The reason why we are still using CPU is not because x86 is the king of CPU architecture and Windows is written for x86, the reason why we are still using CPU is because the kind of tasks that an OS needs to do, i.e. making decisions, is run more efficiently on a CPU architecture. An OS needs to look at hundreds of different types of data and make various decisions which all depends on each other. This kind of job does not easily parallelizes, at least not into an SIMD architecture. In the future, what we will see is a convergence between the CPU and CPU architecture as CPU acquires the capability to work over blocks of data, for examples. Also, as manufacturing technology improves and chips get smaller, the CPU can afford to implement more complex instructions.
CPUs. Virtual memory, means of addressing devices other than memory, for example keyboards, printers, secondary storage, etc., interrupts. You need these to be able to implement anything like a modern operating system. They are also, relatively, slow at double precision arithmetic when compared with their single precision arithmetic performance, and are much larger, in terms of size of silicon. Older CPU architectures don't support indirect calls, through function pointers, needed for most general-purpose programming, and more recent architectures that do so slowly. Finally, as other answers have noted, for tasks which cannot be parallelized, CPUs lose in comparison to CPUs given the same workload. Edit. Please note that this response was written in 2011. CPU tech is an area changing constantly. Things could be very different depending on when you're reading this tongue. Some CPUs aren't slow at double precision arithmetic, such as NVIDIA's Quadro or Tesla lines, Fermi generation or newer, or AMD's FirePro line, GCN generation or newer. But these aren't in most consumers' machines.
A CPU is like a worker that goes super fast. A pu is like a group of clone workers that go fast, but which all have to do exactly the same thing in unison, with the exception that you can have some clones sit idle if you want. Which would you rather have as your fellow developer, one super fast guy, or 100 fast clones that are not actually as fast, but all have to perform the same actions simultaneously? For some actions, the clones are pretty good, for example sweep the floor, they can each sweep a part of it. For some actions, the clones stink, for example write the weekly report, all the clones but one sit idle while one clone writes the report, otherwise you just get 100 copies of the same report.
If you want to support the channel, please consider subscribing.